Okay, so guys, I'm gonna try to make try to take a different tack on the lecture today and make it a little bit more interactive in some parts. So I kicked in, and I'm gonna have some examples examples, and then maybe either have you guys raise your hands um, or I'll call on some of you guys to help me do it, just to keep things exciting. All right, so let's start with, let's do a review. So what we had before was, like, if we're going to we looked at delay. Whoops. Review of delay. And what we said is, for the most accurate calculation of delay, quote unquote, use either simulation or timing analyzer. Because to get the most accurate calculation of the delay, you want to basically solve a bunch of differential equations for all the nodes in your circuit, all the capacitances being charged and discharged by the currents of your transistors. So you need like a simulation tool. You don't want to do that by hand. So that's the most accurate way to do it. But, and this is the reason we're looking into what we're looking at in the class, is that you can't do with simulations. It's hard to do what if analysis. It's hard to do optimization. And it's hard to do debug, basically. If, like, your timing, if you're not meeting timing in your circuit, you just have too many degrees of freedom in your simulator to go and tweak transistor sizes and resimulate, etc. If you're doing that blindly, you're just never going to converge. And it's something that I still do to this day, and I see a lot of younger engineers do it. So that's why it's useful to have a sort of a hand. So that's why we're looking at doing a hand estimation or Excel sheet estimation tool. And that's based on, it's like we said, it was roughly accurate, depending on a lot of dependencies, but it's in the sort of 10 to 15% range, but good enough that it can tell you roughly where you are, how many stages of logic you most likely can have in each process between flip-flops and those kind of things. It's not accurate to 10 or 15% in every point in your voltage versus time characteristics, which, when you look at the overall input to output delay of your gate, it's within 10 to 15%. And the way that thing looked, and I'm going to use an inverter driving another inverter of the same size as an example. Okay, so these numbers are the width of these transistors compared to a minimum size device. So this guy is driving somebody like himself, another inverter of the same size. And what we said was we would have model the PMOSFETs as a resistor with a switch, and the resistance of the PMOS for a unit element PMOS is 2R, but because we have twice the width of a nominal, so I'm just going to make 2R divided by 2. So that's the resistance of that guy. And then it would have an associated junction capacitance And because it's twice the width of a nominal device, it'd have 2 times C. So R is resistance or equivalent resistance of nominal, or sorry, minimum of minimum NMOS. And C is gate capacitance or junction capacitance of minimum NMOS, okay, and PMOS. Okay, so that's what the PMOS looks like. So this is what a PMOS looks like with this 2x width, and an NMOS also looks like a switch and a pull down with just a resistance R, and it's going to have an associated capacitance because it's a unit size. It's a size 1, so it's just going to have 1C. And then we can basically so we want to figure out this circuit that we're designing here, or with this structure that we're putting in, is trying to calculate the prop delay through this first guy. Okay, so as far as that first guy is concerned, as far as this first stage is concerned, the only thing it sees in the second stage are the gate capacitances. So we add those gate capacitances. Okay, so that's this 2C is for the PMOS, and this 1C is for the NMOS. And anyway, so this ends up being the equivalent of this circuit. It's just a bunch of resistors and capacitors. And so if we were going to just sum up all the resistors, so the resistor for the P would just be R, so 2R over 2. And then if we sum up all the capacitors, they would end up being so we end up with 3C for the load and 3C for the device itself, so a total of 6C. And then this is the NMOS. So it's a pretty simple structure. And the delay of this is just, you know, depending on whether you're pulling down or pulling up, ends up being the delay is 6 RC. So basically I'm taking, you know, R, whether it's pull down or pull up, times 6C, and end up with 6 RC delay. Okay, and just a note here is notice that this capacitance, say, is the capacitance of the first inverter. So even if you didn't have a load, you would have this capacitance, even if you weren't driving anything else. So this is called, you'd call this, there's a parasitic capacitance, and it has a parasitic delay associated with it, quote unquote. And this guy is the capacitance of the second inverter, or the load. And so this is, you know, the load capacitance. Okay, so depending on how many devices, you know, for example, as we'll look as an example, this inverter could have a fan out, you know, it could be driving 4 other inverters, in which case it'll see 4 times the capacitance. But in that case, it'll only see its own capacitance. It won't, these guys would stay the same. These would get multiplied by 4. Okay, so this was what we looked at in the delay, sort of summary of what we looked at in the previous slides. But this is just to give you the delay. It's really a starting point because it gives you the delay through one stage. But we're almost never interested in the delay of just one stage. We want to, if I was going to draw a bunch of random gates, I don't know. Who knows? You're trying to get some functionality created in your block. So basically what you want to do is you're almost always trying to figure out what the delay is for this function, overall delay, and optimize it. So really what we want to do is, and this is what this lecture is about, is how to, when you looking at a multi-stage logic network, how do you calculate its delay or estimate its delay, and how do you optimize, figure out what the best number of stages is, and otherwise optimize it. Okay, so that's what we're going to do, basically a multi-stage logic network. And we're going to introduce a couple of concepts. Okay, so here comes the first example that I'm going to first have you guys take a crack at it real quick, and then see if you guys can help me put it together. So, and if you want to cheat, this is example 4.4 in the book. Okay, so it says, so using what we just did, so it says estimate the prop delay for a unit inverter. So here is our unit inverter. For a unit inverter, the PMOS is twice as big as the NMOS to make the resistances the same. The equivalent resistance is the same. So we have the unit inverter driving M identical inverters. So this guy is driving M inverters like itself. And what kind of PMOS drawing was that? Okay. So M of these guys. So basically we want to figure out what the prop delay is using this methodology that we just talked about. Okay. So I'd like to have you guys take a shot at that. As a hint, so these are the steps I would go through, is because you're doing prop delay, it doesn't say fall or rise prop delay, and it really doesn't matter when you're talking about an inverter with the resistance of the P and the N the same. So pick either pull up or pull down, pull up or pull down. So you only have to deal with like half the number of resistors. Okay, 2, figure out parasitic delay components, because basically you got to figure out what the parasitic, the capacitance of just this guy is, and then the next figure out the load delay components. Okay, which is, there's M loads, Okay. And then let me see. I'm going to replicate this. This is kind of what the circuit looks like. Except the only difference is that there are M of these guys of the load. Okay, so why don't you guys take a quick look at figuring out TPD, and then we can work on it together. All right. Okay, guys. So let's try to do this together. Anybody want to volunteer to help me write down the answer?
I only drew like the circuit for it, like with the capacitors.
Nice. Tim, how did you know I was going to pick you if nobody volunteered?
Because usually I'm like the only one that talks, so.
You're also somehow magically at the bottom of the list. So
Oh.
the computer picked you. Okay, well, why don't you sort of like talk to me about like what you drew?
So basically, it's similar to just the circuit diagram that you have right there, but instead of just one line of capacitors coming out for that part that's circled in green, I just have it branching off to like multiple, like just repeat that a bunch of times. That's what I did. I don't know if that's
okay. So you
correct or not.
did a bunch of guys. Is that what you mean? To see.
Yeah, I guess.
Yeah.
I drew it a little bit different, but I guess that's the same thing.
Okay. Okay. Sounds good. So let's figure out the prop delay then together. So I would, I think it's easier for me anyway to first decide if we're going to figure out the prop delay for high going TPH, TPDH, or TPDL. So sort of a falling prop delay or rising prop delay. Which one would you like?
Let's do rising. I don't know which one's easier, but
no, it's they're the
same thing. Oh, okay,
yeah, more or less. Always pick falling, but what the heck? Be a rebel, Tim.
All yeah, right. I missed last week, so I'm not sure. Like,
no. It's the same. It's the same. So if we were gonna all I'm gonna do is I'm just gonna look at this up. It's not really simplifying that much. It's just sort of like looking at this R. Okay. So I'm just going to ignore this guy. So if because this NMOS will be off, so I can just sort of ignore it, and the PMOS will be on. So I'll have this resistor R loaded down with all these caps. So it's just that simple. So first we have, but then I'm going to sort of divide it up a little bit. So first thing is we have, so what's the capacitance of just the device itself? So just this guy. Just this guy. What's the capacitance? So that would be the.
Oh, sorry.
No, sorry. That would be the parasitic, capacitance.
Oh, is it not just 2 + 1, like 3C?
Yep. So just this guy. So we would just put in 3C for that guy. Okay. So the next question is then what is the load delay capacitance? So what is that? Then you want to give me that as a function of M. So it'd be M of these guys, right?
Yeah, so it'd just be 3C times M, right?
Yep. 3C times M. Okay. So if we were going to just look at the delay from the RC delay, so delay or same as a prop delay, what would it be? Look at, so delay is just, the R's and the C's, right? Want to take a shot at the delay? So just the R multiplied by the C's.
Yeah, I don't think you can add, well, hold up. You would probably have to factor out, so if you add those two, 3C plus 3CM, you'd have to factor out a 3C. So it'd be, I think it'd be R times 3C, and then parentheses 1 plus M, I think. Just doing that in my head. Yeah,
Yep.
That looks right.
Yep, you got it. Okay, great. So what does this tell us? It's basically telling us that as we increase the number, if we have the device driving devices like itself, as we increase the number of those gates that we're driving, we would linearly increase the delay. So thanks, Tim. Is it Tim or Timothy? Which one should I call you?
I mean, Tim is shorter, so I usually just go with that.
Good. Okay. Cool. Okay. Thanks, Tim. So let us do the next example. Again, if you want to cheat, example 4.5 of the book. And then, so we want to repeat previous example. With if the driver is W times larger width. Okay, what does that mean? That means this guy, the driver, instead of being 1 and 2, it's 2 times W wide and 1 times W wide. And then it's driving a bunch of still minimum size 2, 1. Okay. So now we're looking at that. So we want to go faster, presumably. So we made this wider devices. There's no point increasing the length because that just slows you down, right, without any benefits. So we made them W times wider to get more current. So because these guys stayed the same, you have the same load as you did in this case. You're just making your inverter wider, both the N and PMOS by W to go faster. So once you guys take a shot at that, and you could go through the same 3 steps. Okay, let's take a shot at it. Okay, as my next victim, I'm going to pick Haley because she also asked questions.
Oh, I feel a little bit lost with this problem, so I feel like I'm not.
Perfect. That's what we need, somebody who's lost. Come on, Haley. Let's jump in here. So where were you lost at? Or were you lost in 4.4? Did you figure that one out?
After you explained it, I could understand it, but I kind of struggle with this, especially with not the T. I understand how to calculate the T, but more so how to break down the circuit, if that makes sense.
Yeah.
To translate it to the resistor and the capacitor.
Got it. So do you get, let's see, did you get this part? So do you have a problem jumping from this to this, or do you have a problem with this?
I have a problem with that. I have a problem translating it from the original equation to the capacitor sense. But
so from this guy to this guy?
Yeah.
Okay. So let's do it. If you have a problem with it, I guarantee you a lot of other people do too. So that's the whole purpose of this exercise. So let's do it. So remember that or you probably don't remember, but so what we did was we said an NMOS. Oops. So, and then stop me if you remember the stuff or like this isn't what you had struggled with. We said we would take an NMOS and we're going to call it a minimum size NMOS. So for example, in our process, which was, going back to the layouts, it would be the width would be 4 lambda and length would be 2 lambda, say, whatever it is, some NMOS, like the minimum size you could draw.
Okay.
And to make it a simple model, sorry, did you say something?
Oh, no, I just said, okay. I was just agreeing with you. Sorry.
Gotcha. And so, whatever it is. And then we said, okay, so if you do that, and we're trying to create a simple model to do some hand calculation, get some rough ideas. So we said, okay, what we'll do is pretend that like that's just a resistor with a switch. So the switch would tell you if the resistor is, connected or not. And then we would have an R equivalent. Okay, the R equivalent would be different for each process. But it would represent the effective resistance of that NMOSFET. whatever that means. Now, remember the N MOSFET, when it turns on in an inverter, it does all sorts of crazy stuff. It goes into saturation mode, then it goes to linear mode and all that stuff. And our delay model that we're creating isn't to fully model each step along that process, but the overall delay. So it's saying, well, if I look at all those things, I can estimate an effective resistance that, given the RC network, would give me close to the same delay as like a really complicated transistor model. So this is an R equivalent model. And just to throw out a number, we'll see later, would be different for each process. So for example, in a sort of a 65 nanometer process, let's say TSMC's, this R equivalent would be 10 kilo ohm. So this would be like a effective resistance for a minimum size NMOS. And if you had an NMOS that was 10 times as wide as your minimum, its resistance would be 1 kilo ohm. It would be, so if you had an NMOS that was K times the width, so the width was K times 4 lambda, you wouldn't, in digital design, you never touch the length because it just doesn't give you any benefits. Okay, so if it was the K times 4 lambda, you would end up with R equivalent over K. The wider it is, the lower its effective resistance because it's just pumping up more current and it'll drive an equivalent capacitance faster. So
Okay.
you're with me?
Yeah, no, I'm with you. So
Okay.
Thank you. Sorry.
Sure. Yeah, no, don't be sorry. Like this is helping us bring the whole class up to speed. I guarantee if you're lost, so is like everybody, a lot of other people. Okay, so let's just keep going. So it has this resistance, the equivalent resistance, and then we have the capacitances also on the gate, the drain, and the source. And we said, okay, we will add those capacitances and we'll pretend like they're all the same value because this is a hand calculated model. So we're going to say the capacitance of the drain is C, the capacitance of the source is also C, and then we have a gate capacitance that is also C. Okay. And then because as you make this device wider, all those capacitances will also get larger with the width. We would make these C's. We'll go up by, W. It'll be K times C. So if you had, and then we said the C equivalent, the C is, we didn't say this, sorry, but just throw out a number as 0.1 femtofarad for the same 65 nanometer process. Okay, so here if you had, a minimum size device, it would be 0.1 femtofarads on the drain, but if you made a 10 times larger width device, it would have more resistance, but it would also have more capacitance. So you would have 1 femtofarad, 10K would be 10, and C would be 0.1. And same with the gate. The gate would also be K times C.
Okay, I'm following you.
Okay, and then the PMOS, same deal. So the deal on the PMOS is that it's exactly the same, except its resistance, because the mobility of the PMOS is half the mobility approximately of NMOS. Its resistance is actually...
Oh, someone asked a question in the
okay, thanks. Chat. Tim? Who asked the question? Is it Tim?
Oh, I was just seeing if anyone else knew.
Oh, knew what?
Is the K just a constant for the
Yeah.
PMOS and NMOS. That's what I figured, but
Oh no, I mean I'm just using it as let's say if I have a minimum size device, let's say the length is, for the sake of discussion, say its length is 180 nanometers and the width is 300 nanometers, say. Okay. So, and then I have another device. Again, we don't want to touch the length, and the width is 3 micron or 3,000 nanometers, right? So we made the width 10 times wider, right? The K in this case would be 10. The K in this case would be 1.
oh, okay. So it's just a scalar.
It's
Like
just
you're
a
saying.
scaling factor, yeah. So what we're saying is if you may scale the NMOS so it was K times wider, its resistance would go down by a factor of K. So it would be pumping out, K times more current. But also its capacitances would go up by a factor of K, because the gate is 10 times bigger, the drain is 10 times bigger, source is 10 times bigger.
Okay. Yeah, that clears it up a lot, actually.
Okay, great. Yeah, I think the K factor confuses a lot of people. Okay, so back to Haley. So PMOS, the only difference between the PMOS and the NMOS is because the mobility of the holes is less than the mobility of electrons. We said, a default PMOS is going to have, so it's going to have a equivalent resistance of 2 R equivalent. So it's going to have twice the resistance. So the same width is equal to 4 lambda, L equal to 2 lambda. PMOS is going to have twice the resistance of the same size NMOS. But the capacitances would be the same. So it would have the same C. It'd be the switch. It would have the C, and the gate capacitances would also be C. Okay, and if you made your PMOS, same thing. If you made it K times wider, so if you made a device that was K times 4 lambda wide, then you would end up with R, whoops, sorry guys, my handwriting is just awful. 2 times R equivalent divided by K. K times C for the source, and K times C for the drain, and K times C for the gate.
Okay, that makes sense.
Okay, so having said all this, so now we are back to the first problem. We had so we had this circuit. And the 1 and the 2 are representing the fact that the NMOS is the same as a unit NMOS size. And the PMOS is twice the unit PMOS. And the reason we made it twice as wide, so that it'll have the same resistance as this unit size NMOS. So
Okay.
our pull up and pull down pop delays are about the same.
Okay. So that makes sense. All right.
And then it's driving, let's say it's driving its own twins size stuff, its own size, and it's driving M of them. So basically, I'm just gonna now take this, and draw that. So for the PMOS, I'm gonna have, noticed it's 2 R equivalent, and the K of the PMOS is 2. So that's why I have 2R equivalent over 2. Okay. The source of the PMOS is this particular PMOS. Its source is connected to a supply voltage, so it's not going to, this capacitance won't matter. So I won't even bother drawing it. But the drain matters. And so I'm just going to push this up. Doesn't matter the capacitance, whether it's connected to VDD or ground. As long as it's a DC value, it'll just sort of show up in your RC. So this is K times C, and again, K is 2, so it'll end up with 2C. That's this guy here, with K is equal to 2. Okay, so that's my PMOS. Okay, and then my NMOS is it's R equivalent. The K for the NMOS, so it's N, this guy. Where are we? This guy with K equal to 1. So
we'll just make it R equivalent.
Yeah, R equivalent. And then the capacitance, again, is K times C, and K is equal to 1, so it'll be 1C.
Okay.
Okay. And then, so that's the guy itself. And then let's look at one of these guys. If it's driving one of these guys, all it sees is the gate. So all it sees is this capacitance as far as our circuit's concerned. Okay, so it'll see the gate of KC, where the N MOSFET of what it's driving, one of those guys is driving, is 1C, because K is 1 for that guy. And then for the P MOSFET, it'll see 2C, because the K for the PMOS is 2. So for what is driving for one of those guys, there'll be 2C and 1C for one of these units. But then we have a bunch of these guys. We have M of these guys. So we'll have M of these loads.
Okay, I see.
Okay, so this was 4.4. Okay, so 4.5 is what it's asking is, what if I made this guy W times wider?
So then it would have W times the top of the R equivalents, as well as multiplying the capacitors. But it wouldn't affect the drivers at all, would it? Or what it's driving?
Yeah, it wouldn't affect the drivers at all. That's the problem, is saying keep those constant. And exactly like you said, it would basically multiply this guy by W if you're looking at the pull-up. So if you're going to drive, so let's say we do the same thing as we did with Tim. We pick TPD rising. Then we would just look at the P MOSFET. So the resistance would be 2R equivalent over 2 times W. Okay, and then it'll have a switch. You switch to the PMOS. And the capacitance would be 2CW. Oops, no, sorry. The switch is closed because we're pulling up. So the switch is closed. And you'd still see the capacitance of the NMOS. So that's 1CW. But you wouldn't see the resistance of the NMOS because that switch is open because we're pulling up.
Yeah.
Okay. And then we see all the same loads. So we would have 2C and 1C for each load. Okay, so that your total is 3C, but then we have M of them. So the total load you'll see is 3 MC.
Okay, that makes sense.
Okay, so now let's see, what was this? What was we going to do? We're going to figure out the delay equation. So what's, I guess the first thing to do is this is the parasitic. So this is the parasitic. So first, once you take a shot at, let's do the TPD, right? So once you give a shot at like coming up with our equation for the delay, which is just the RC delay.
Professor, I had a question.
Yeah.
So you said we are like raising the size by W, then wouldn't it mean resistance would be divided by W instead of?
Oh, thank you. Yes, you're 100% right. Thanks for catching that. Thanks.
Sure, no problem.
Haley, you want to give a shot at doing the RC? So first
sorry,
we have, what's that?
Oh, I was just changing for the W. Okay.
So we have, this is our R.
And then we're going to be adding together the capacitors. So it'd be 3 CW.
So,
and then plus, would I be adding the 3C with the 3 MC?
Yeah, so you'd have the 3 CW for the driver itself, and then you'll have the 3 MC.
And then plus the, oh wait, sorry, yeah. And then times the R over W.
Right, so it's R equivalent over W.
And then
yep,
you could take out a 3C, and then you'd be left with W plus 1 plus M, or 3C R over W, and then a W plus 1 plus M.
Let's see, 3C.
Oh, wait, oh no, sorry, I had an extra one. Sorry, it should be just W plus M.
W plus M. So wait, sorry. Let's calculate these. Let me see what we ended up with, Tim. How did we put it? Because I want to compare it to this one. So we took out the 3 RC in the case of in that first one. So let's do it the same way so we see how it changed. So I'm going to have 3 RC out here. Okay, so I took out the R, I took out the C. So here I get, in this first term, I get just W.
And then plus M. But then would we have, if the R is divided by W.
Yeah, so you'll just end up with 1 here.
1.
W over W.
And then plus M. Okay, so you end up with the same equation regardless of your width changing?
So what happened though, look at it, look at this.
Oh, sorry.
So the W divided the load by W.
Okay.
So what happened was this is the parasitic part. This is like driving yourself. And this is the load part. Okay. So if what this is telling us is if you make your driver W times wide, so make it wider and wider and wider, it's not gonna get, just driving itself, it won't get any faster, because as you're making that driver wider, you're reducing its resistance, but you're increasing its capacitance by exactly the same ratio. So So if it's not driving any external loads, you make that thing wider, narrower, whatever, it doesn't matter. It's something that's W times as wide. It will have the same RC time constant as something that's, just your unit one. But what it will do is it'll drive loads better. So what it does is it makes it look like the load is W times less big than it would have been for a smaller driver. Okay, so your self speed is like sort of you have this minimum, I guess is the way to look at it, this 3RC. Like no matter how wide you made your driver, you're going to have at least that delay. And if you make it wider, smaller, that won't change. But it'll give you the ability to drive a load better. It'll make the delay of the load less and less.
Okay.
Okay, great. Thanks, Haley. Thanks for being a good sport. All right, so let's, let's try another example. Whoops. What am I looking at? Oh. Just give me 1 second, guys. Huh, okay. Sorry, guys, I'm just trying to look at the right. Okay, good. I'm back to the correct file here. So example, so again, if you guys want to cheat, example 4.6 in the book. So now it's saying, okay, now it's going to give us the actual, says, let's say we have the same situation as a unit size inverter. So a 2 and a 1, driving 4 other guys like itself. Four of these guys. Okay, now it's actually saying, okay, this is in a 65 nanometer process, and R is 10K ohm, and C is 0.1 femtofarads. Okay, so it wants to calculate the delay in this case. Okay, so once you guys take a shot at this, and this is, look at this, this is exactly like 4.4. It looks exactly like this case, but it's giving us the M here. Okay, it's telling us we're driving 4 inverters like itself. Okay, so give that a shot.
Is femto 10 to the negative 15?
Yes, it is. Yep.
Okay. I get confused between pico.
Yep. I think after that is like atto or something. Okay, guys. So, of course, Nirupan put himself in my crosshairs. So, Nirupan, can you help me figure this one out?
I'm just trying to do the calculation, but I think it's just 3 times RC times 5.
Okay, so you think it's 3 times RC times 5.
Yeah, because in the parentheses it was 1 plus 4, so you plug in 4 and you get that.
So you basically took this
equation. Yeah.
So let me just do that real time. Okay, so basically you said m is equal to 4. So we end up with 3 RC times, oh, yeah, m equal to 4, so we end up with 5, right?
Yeah. So it'll just be 15 RC, which is 15 times 10 times 1 times 10 to the negative 15.
10 times 10 to the third ohms times 0.1 times 10 to the minus 15, right?
Yeah.
Okay, and so, you know, so this guy takes out this dude. So, and then 3 times, we got 1 10 to the third here and 10 to the minus 15 here. So you end up with a 10 to the minus 12. So you end up with 15 times 10 to the minus 12 or 15 picoseconds. Okay, so that's the delay in the 65 nanometer process. Which is pretty fast. So I think, you know, this, if you thought about like how many times this could transition between 1 and 0, so how many times it could switch in a second, it would be something like 66 billion times. So if I take f is equal to 1 over this t, so 1 over 15 picoseconds, it would be 66 billion times per second this thing could go. It's a lot of switching. It's kind of fun. Thanks, Nirvan. Okay, so hopefully that gives you guys a feel for this model that we've created and kind of what kind of numbers you might end up with. Now, so this was for a 65 nanometer process. As you go to older, so bigger processes, like if you went to a 180 nanometer process, you know, R might be, ends up being, I think that's kind of like what we're using. R ends up being about, I think, 2 kilo ohms. And F is like, sorry, the C is maybe around, I don't know, I don't remember what it was, maybe 2 femtofarad-ish. Okay. And then if you go to, I'd hate to guess this 45 nanometer process, the R gets larger, but then the C gets smaller faster. Okay. So, but basically what you can do is, the nice thing about this approach is, notice if you have this kind of circuit, let's say you have a case of an inverter driving another 4 inverters like itself, you'd always have this equation 15 RC for that, for the delay. Excuse me. You just change the R and the C depending on what process you're in. So for example, that might be, in a 65 nanometer process, this delay might end up being 15 picoseconds, or in a 180 nanometer process, that might end up being like 60 picoseconds or something, depending on what the R and the C is. So nice thing is you can have the same equation, you just change the R's and the C's, depending on the process that you have. And for example, your book on, I think it's table 8.4.3 or something like that, chapter 8, it's got like a bunch of different processes, and then the R's and the C's for each one of those that somebody calculated, and you just kind of use over and over again to estimate delays. Okay, so that's coming up with a delay of a single stage. That's where we've been so far. But in, like I was mentioning, in every case, what you really want to do as a designer is to figure out the delay of some, you're trying to implement some logical function. That's, as a designer, that's your first step, is figure out, okay, I need this logic to implement this particular function. Now I want to see how fast will that logic go in a particular process, or you want to see how should you size these different devices so it goes as fast as you want, or how to optimize it. So that's this next step that we're going to be doing, and this is called, I think the book called this the logical effort. But basically the idea is, this kind of thing. So I want to have it back of the envelope calculation to figure out like these kind of things. How many stages of logic can I stick between 2 layers of flip-flops, given that I'm in a particular process and in a particular clock speed. Okay, so where this is useful, because it's like I think I keep having to say this, because the tendency is to think, what, I'll just implement what I have and I'll simulate it. There are all these great simulation tools available. I'll just stick all these logic gates into my simulator and figure out, it'll tell me what the delay is. Why do I need the hand calculation, or why do I need sort of a hand or Excel estimation tool? The problem comes in, let's say at the beginning of the project, right? So at the beginning of the project, you haven't designed the chip yet. So that approach is okay when you've designed the chip. But let's say at the beginning of the project, you're trying to negotiate with your customer. Your customer doesn't want to pay for an expensive process. They want to pay for the least expensive process that'll meet their requirements. And you don't know off the bat whether that process with the functionality that they're looking for is going to be fast enough to meet their requirements. So right off the bat, over a matter of like 40 person hours, or like a week of work or several days of work, you want to have this discussion with your management or your customer that says, hey, look, I don't think we can design this in this particular process. We might have to go to this other process, or we might need to make this functionality simpler. So this is, the level where you need these kind of things at the front end of your design. Because by the time you've actually done the full design, it's too late. You're already, everything's already been decided, and you don't want to, at that point, to realize you're trying to fit a, square peg into a round hole. You want to do it with some simple techniques before putting in all the work to figure out, give you a sense of direction or optimize things. So that's the whole idea behind this logical effort. And here's an example that the book gives, that after, we're just going to describe the example here, and then at the end, come back and see how we can use this logical effort to calculate it. But basically the idea is that you have what's called a register file, which is just another name for a memory. Okay, the memory is 32 bits wide, and it has 16 words. So it has 16 words, each one of which are 32 bits wide. I don't know, I'm going to write 32 bits. And you're going to have 16 of those. Okay. And a decoder is basically a function of, it takes, a certain input. So A through 0 through 3. So this means A 3 to 0. I'm assuming you guys all know that kind of lingo. It's just a 4-bit bus named A. And basically that'll go between, all zeros. And let's say it goes, if it does this. So, oops. So I'll have, 16 possibilities. And then the output of this decoder is 16 bits. So you basically want to select, for each one of these 16 inputs, you only want to select one of these 16. So if I look at the output, we'll have, 16 bits, and then the first one will turn on. And then, we'll have 16 bits, and the second row will turn on. And the third row will turn on. And, the fourth row will turn on. Okay, so that's the functionality of a decoder. So, he's trying to build this decoder, and there is a certain capacitive load that these bits have. It has a 3-unit transistor load in each bit. Okay, so I think he's trying to decide, how does he design this decoder, how he should size the gates, and how fast he can get it going in any particular process. So again, this is at the front end of the design, where he's trying to make some like directional choices. So he doesn't really have anything to simulate yet. He's just trying to figure out, these parameters, so he can get the starting point, either with discussions with his management or to get the design started. Okay. So anyway, that's the kind of, so we're just describing this example as something that's a fairly simple thing, but it's not unusual to be in a situation where you're designing a decoder, but you have a bunch of degrees of freedom and uncertainty. Okay. And then once we describe this approach, we'll come back. Okay. So this is the description of the approach, which is following up from a single stage delay. So what this approach says, this is the same thing we said before, which is the delay has 2 components. One of them is caused by yourself. So it's calling that the parasitic delay. This is the capacitance of whatever device is itself. And then F is what's called the effort delay. That means the effort to drive a load. Okay, so it's got those 2 components. So some of this you guys are going to have to just trust me because it'll take a couple of steps before we get anywhere interesting. But so anyway, we have those 2 components. Okay, so first the parasitic delay. It basically, again, is your own, without driving a load, okay, we want to know this is just a delay without driving a load, okay? And in this activity, everything is referred back is referred back to unit inverter. Okay, so everything is referred to this guy, our unit inverter, which is, you know, we got a minimum size N and a 2 times minimum P. Okay, so for example, this minimum inverter, its parasitic here is gonna be, you know, it has, I'll draw this in green. It's got 2C for the P and 1C for the N. So the parasitic capacitance here is 3C. Okay, so let's say you have, I'm gonna calculate all these for a, let's say a 2-input NAND, okay? So I have a 2-input NAND. So first thing I want to do is to say, okay, this thing, if it had the same pull down and pull up resistance as my unit inverter, what would be the size of these devices? Okay, so because the N MOSFETs are in series, I need to make them twice as wide. So their total resistance ends up being 1. Okay, and the P MOSFETs, because they're in parallel, I can just keep them the same. So I'll make those stay at 2, 2, 2. Okay, so let's look at the parasitic resistance of this guy. So the P MOSFETs will have 4C for the P MOSFETs, and the N MOSFETs will have 2C, right? So because you just see this guy. So this P, this P is equal to 6C. Everybody with me? So, or
Professor, I didn't get where you're getting the 4C from.
oh, thanks. So this P MOSFET will have 2C of capacitance, and this P MOSFET will have 2C of capacitance.
Oh, okay.
So together, they'll have 4C of capacitance. And then this N MOSFET, because it's twice as wide, it'll have a 2C of capacitance.
Okay, so we're still not doing anything with the capacitor at the very end, right? The one that says B?
The one that says what, sorry?
The one that says B, like the one that's at the very bottom.
Oh, here?
Yeah, that one.
Yep, we're just looking at the capacitance of the drain.
Oh, okay. Thank you.
Sure. So the P, okay, for in this methodology. So just got to follow me. Is this the ratio of this parasitic capacitance of this device for a NAND gate compared to a minimum size inverter? So P is equal to 6C divided by 3C. So it's equal to 2. Just a ratio, everything in this methodology of looking at delays, you're just referring everything to a minimum size inverter, to this guy. Okay, so I'm going to basically like scale everything. So we're comfortable with this. So we're just saying, hey, if I have a NAND gate, it'll have, if it has the same drive as this guy, they'll have twice as much parasitic delay.
Professor,
yeah.
How come the width for the PMOS and the NMOS are the same? Isn't the PMOS supposed to be double the width?
Yeah, so basically what we're trying to do is have this 2-input NAND gate have the same drive as this inverter, okay? So if you look at the pull-ups, right, you could have this on or this on, right? So they'll have the same pull up strength as a PMOS for the inverter, okay? But the N MOSFETs are in series. So if I want the pull down resistance to be the same as this pull down resistance, so 1, I need to make these guys twice as wide because there are 2 of them in series. So the equivalent resistance here on the pull down is the same as this one guy.
Makes sense. Thank you.
Sure. So basically you start by trying to make your pull up and pull down resistances the same as this minimal guy. Guys, I think I'm going to stop it here because, we're just we got a lot to do here before this starts making sense. So I'll pause it here and then we'll start again on Thursday. Any questions on what we talked about so far?
None from me.
Okay. Well, how was this? So, I warned you guys. I was like starting to get antsy about how the lectures were going, and I was going to switch things up. How was today? Was it better? I mean, it's kind of putting you guys on the spot, and that's never comfortable. But does it? Is it a thumbs up or thumbs down? How did you guys feel about that?
I think the more interaction is good.
Yeah.
I think, maybe if people want to submit answers first, it would also be good. But I think it's good as well for everybody. There's more involvement and people feel a little more antsy, so which is good because then you want to pay attention more.
Yeah, you want to feel antsy now and not during the test.
Yeah.
Yeah. Okay, sounds good, guys. So we'll just keep going with this, and then we'll tweak it as we go. So anyway, if there aren't any questions, I'll talk to you guys on Thursday.
All right. Thank you, Professor.
Thanks.
Have a good one.
Take care. Bye.
Professor.